Welcome to our repeatable vehicle presentation for scenarios week 2.
For the 2021 IMechE design challenge, our task was to design a repeatable vehicle that would drive up to a wall and then reverse to its start position. During scenarios 1, our design focused on the accuracy of drive, and you can see our design in this image. However, for this scenario, we have aimed to minimize both the time taken and energy used to complete the run. This must still all be done by a vehicle costing less than 30 pounds and smaller than 400 by 400 by 400 millimeters.
In both designs, distance is measured mechanically by moving the tape from a full reel onto an empty reel. When the vehicle contacts the wall, a DPDT switch reverses the polarity of the motor, sending the car backwards. As the car reverses, the tape then travels back until it reaches its start point, where a strip of foil adhered to the tape contacts two wires, which complete a circuit that stops the motor. After consideration and physical testing to check the validity of the idea, we chose to use a cassette tape rather than build our own reels, as a cassette fulfilled all of our requirements, including strength.
Thanks to the simulator, we managed to study how different parameters affected time and energy. Firstly, we saw that reducing mass, especially rotational mass, led to smaller energy consumption and improved times. We also confirmed that decreasing the gear ratio would vastly improve time to the expense of little extra energy. The simulator also allowed us to determine that the spring constant had a negligible effect on energy and time. To further determine a gear ratio, we analyzed the speed values given by the simulator. We checked using our own MATLAB impact simulator that the g-forces experienced at impact didn't exceed the previously calculated maximum.
To reduce mass, the first step was to use nylon nuts, bolts and washers instead of steel ones, saving us more than 61 grams. Changing from steel to carbon fiber axles further reduced the mass by 32 grams, and a big redesign of the laser cut chassis was completed to remove unnecessary material. In total, more than 200 grams were saved.
Simulator testing showed that reducing inertial mass was very important. To minimize the wheel mass whilst ensuring adequate strength, generative design was used, which utilizes finite elemental analysis to identify areas which can be removed whilst causing minimal structural disruption. The additive manufacturing process was inputted as a consideration into the Fusion 360 simulation so that the design is suitable to manufacture given the layering process of 3D printing.
The alignment system was identified as an area of improvement after the first scenarios week. A laser is used to help line the cars up straight with the track by aiming the laser on the center of the targeted wall. To improve the alignment of the car as it runs down the track, the steering angle of the front axle is adjustable up to 10 degrees, so can be varied to account for any observed deviation.
We have increased the length of the vehicle to the maximum allowed length of 400 millimeters, with a boom to reduce the distance it needs to travel. The gear ratio has also been modified so that the car can travel faster.
Using the pricing system from the IMechE, we found that the total cost of materials for the vehicle is £26, and excluding parts less than 20p, it is £19. From 3D printing our own wheels, we saved £7.96, which allowed us to pay for lighter materials such as carbon fiber axles and nylon fastenings.
Furthermore, we wanted to compare the simulation results with our own MATLAB code. We had a small 370 millisecond difference regarding time and a 0.2% energy difference. The simulated speed was 0.04 meters per second different to our expected value. These are all small differences, which leads us to believe that our own code is a suitable model. Yet we know that our model provides us with vastly more information, such as RPM, impact forces, and acceleration.
In our final results, we can see in the above graph that energy used increases mostly linearly, with a jump in the middle whilst the collision is happening. At the bottom, we have the graph for acceleration during the collision, which reaches over 20 meters per second squared, which our MATLAB model showed us was low enough that the car would not skid. In the end, this brings us to a total runtime of 9.23 seconds and 0.61 joules of energy used.
Thank you for listening to our presentation, and we look forward to your questions.